Good to see you all again. It's been a couple of weeks since we had a class, so I hope it doesn't feel too long ago. It's just the nature of this particular module where we have a few blocks and then also regular classes, that the regular classes sometimes get a bit spaced out. I think that works okay usually in my experience. But, you know, keep feeding back on it. And if there are things that aren't working okay, then we can try and fix them. A second thing is that just in the last 10 days or so, the internet in my house has suddenly started being less good than it was. So I get some messages that say I'm having bad network quality. I hope that doesn't interfere with the class, but we'll just have to see how that goes. And I can only apologize for it. Let me just share my screen a second, if I can. So this is what we were working on the last time. These slides on joints and connections is what I've called it, but it's kind of a catch up on a few different ideas that we're going to need now in order to move into what happens in sort of full structures. And that's what we're headed towards, is that discussion of complete structures and how we can analyze those. This slide was really important, so I just wanted to come back and visit that again from last time. The idea that you can have simple supports which provide force in one direction. You can have pin joints which provide a force in two directions. And you can have clamped joints which provide two forces and a moment. And again, the more you work in fusion, the more things like this will start to make sense, I think. So, you know, you'll be putting these in as ways to describe the joints that you use in fusion, and then you see where they push back and where they don't. And the idea is that these things aren't just artificial things we draw on a diagram, they're things that occur all around us in real life. And so that's what this slide is really about. And then there were some examples and some questions. And again, part of the point here was that we turned everything back into a mathematical analysis, so we could do things like analyze the reaction forces at the wall here. And of course, that might tell us in turn something about whether this whole structure was going to fall off the wall, or whether the wall was going to break, or whether the arm was going to bend, the beam was going to bend, for example. So those are the things that we were interested in last time. I'll just stop sharing for a second to say, any questions around any of that? Does that match your memory of what we talked about and your understanding of where we've got to?
Yes.
Okay, cool. I will, thanks, Harry. And just to say as well, as always, I'll be keeping an eye on the chat where I can. So feel free to put things in the chat if that's a useful way to go. Okay, this week we've got one topic that we want to cover, and it's quite a big one and quite a difficult one, I think. So let's get started on it. The thing I will say is this is really, as far as we go with this analysis and using Newton's first and second laws, or particularly Newton's first law, that if something isn't moving, that means the forces acting on it must be in equilibrium. That kind of reaches its peak of use for us today, and then afterwards we'll move on to some other things. So I guess in some ways this lecture is the most complicated content of the year in this module. So what we want to look at today are truss structures. And by that, I mean things like what's on the screen here right now. And once you start looking at these things, you start seeing them everywhere. Obviously, two of my examples here are bridges, because they have these kind of triangular trusses that lend themselves very well to engineering analysis. But I mean, I'm just looking around me, and we could use the same kind of understanding to match the shelves that are next to me right now. To analyze the shelves that are next to me right now, or to analyze the chair I'm sitting on, for example. It's another one of these things where everything is a truss structure if looked at in the right way. But the word truss means in particular, in this case, that it's made up of long, thin elements all connected together. So I hope that's what the next slide says. Slender members, and by member I mean like one of these arms, and that's a word we'll use a lot in this context. Joined at their ends, so something like the picture that we're looking at here. Loads are applied at the joints, that's going to be important, and members are joined by smooth pins. So at the joints, things are free to rotate, and that means each member could be in compression or it could be in tension, but it can't sustain an internal shear force, for example. We'll come to things next year that can do more complicated analysis, and in fact we'll come to a bit in the next lecture where we need to think about internal shear forces. But within these trusses, everything's either in tension or it's in compression. So the first thing that I want to look at is called the method of joints. And in the method of joints, we look at each joint of a truss in turn. So by the joint, I mean basically where the pin is, where the members all meet is a joint. And at each joint, we know all the forces that are acting on the pin, and then we know that the pin isn't moving, and so the pin must be in equilibrium. So I can look at this picture here and write down a set of equation, or a single equation, which must be true about F, FAC and FBC. They somehow have to all balance out. And in fact, we can get two equations here for this pin, because we know it's not moving horizontally and we know it's not moving vertically. So we can run some calculations and this free body diagram to find out two unknowns. And that's really the kind of analysis we're going to use for the first bit of this lecture. This slide is kind of an aside. You can ignore it if you want to, and you'll be all right. But sometimes you can immediately see that some of the members aren't really doing anything to support the forces. So in this example here, CD, if there was a compression or a tension in CD, there'd be nothing else to balance it. There's nothing that can provide any other horizontal force on this pin. So there can't be any horizontal force in CD, otherwise the pin would move. And similarly, if BD was providing a vertical force, there'd be nothing else to balance it, except I guess the weight of the pin, but we tend to ignore the weight of the structure itself. We're saying it's a lightweight structure supporting a heavy force. So the weight of this bit doesn't count for anything. There's nothing pushing down on D, so BD can't do any pushing up, for example. And that'll make more sense, I think, when we go through some examples, but it's just an idea to be on the lookout for. Okay, so what I've got here is an example straight away that we're going to work through. And I think because we're just getting started out on this, I want to work through it as a group. I'll put up the visualizer and we can do it all that way. But I just want to give everyone 3 minutes now, first of all, to draw out the diagram and to make sure you're happy with that. And then also just to think about some aspects of the problem that you can understand and maybe mark onto your diagram or start analysing initially. And then we'll do the truss analysis bit in, as I say, 3 minutes time, if that's okay. So while I'm asking you to do that, I'll also just draw up my version of the diagram here. I can't see a way to get a kind of full screen in half a screen, so we'll have to accept it like this for now. Okay, that is 3 minutes. So let's just kind of start talking through this question and see how it goes and how we get on. I've drawn out my diagram here, and I hope everyone can see that. What else can I mark on to this diagram? I guess the thing that I'm interested in is this is a force acting downwards on the whole structure. So there must be somewhere a force acting upwards on the whole structure. Otherwise, the whole structure is going to move. So always one of the very first things you can do in these analyses is, before we get into looking at what we'll call the internal forces, the forces inside individual members, we're going to look at the external forces, the forces actually acting on acting on the whole structure. And so just like if this was a single beam, this force here acting downwards must be kind of balanced out by forces acting upwards at these two supports. And just by the symmetry of the situation, I hope people can see probably that these two forces are going to be equal. That would be 30 kilonewtons acting upwards at both of the supports, and that balances the 60 kilonewtons acting downwards in the middle. One of the things, I guess, that isn't said in the question as it's shown here are dimensions. It'll turn out that as long as we assume the the vertical and horizontal bars are all the same length, it doesn't really matter what the dimensions are. But we are assuming here that this 60 is bang in the middle of the 230s. Otherwise, if you move this force here over to the left, you'd find that more of the load was supported on the left-hand side. And that's the kind of thing that's in some of the tutorial sheets that are available just now for this module. Okay, so I've got now some forces marked on my diagram, and I next want to make sure that I start looking at individual joints, just like in the diagram that started out these slides that I'm working on. You've got 6 joints on this image, A, B, C, D, E, F, and I can look at any of them in turn. And I'll be able to solve the problem no matter where I start. But as you start to get familiar with these things and these ways of working, you'll see that sometimes it's easiest to start with the simpler joints where there's less going on. So for example, I don't really want to start at E up at the top here because I've got 1, 2, 3, 4 members connected to E, and each of those could have some force in it, and so I'd get some there, but I wouldn't necessarily get any of those member forces solved by looking first of all at E. Whereas if I look at, well, F is an interesting case. I think it's going to be one of those zero force situations, just like we looked at in a previous slide. But let's start by looking at F, and then we can see how this kind of analysis goes. The more of it we do, the more it'll make sense, I think, is the key. So don't worry if at first it feels a bit unfamiliar. By the time we solve this whole problem, I think you'll be getting a feel for the analysis that we're doing. So first of all, let's just say we're going to look at F on its own. The first thing I do is to draw the pin or the joint, and then to mark on the forces that can be acting. I'm going to always draw the forces as pointing away from the pin. So that's kind of making the assumption that there is a tension in each of the members. It doesn't really matter if I'm wrong. If there's a compression in the member, I'll just get a negative number out as my answer. So as long as I stick to one convention and then say, okay, positive numbers are tension, negative numbers are compression, I'll be okay. So this is the TEF, I'm going to call it, the tension in EF, and this is TAF, the tension in AF. And those are the only forces that can be acting on the pin at F. There's nothing else going on there. We haven't marked on any forces around F, and there are no other members that could be providing a force. So now we always, once we've drawn out that free body diagram, which is what this is, then we always do the same thing, which is to resolve horizontally. And that is saying, okay, all the horizontal forces have to add up to 0. So, or equivalently, forces acting to the right have to add up to forces acting to the left. And what we'll get is that TEF must equal 0. And similarly, we can say, okay, the vertical forces also must add to 0, and that means TAF equals 0. Has the camera frozen? I'm not seeing any network problems on my end, but can people see me?
It's just like really slow for me.
Okay, what I'm going to try doing is just
actually mine shows the camera up, yeah.
Okay, so it's working, but it's got some problems. I'm just going to try connecting. No, I'm connected to the right Wi-Fi as well. So I keep doing the same thing if you can. Post in the chat if it's not working, and then I'll try and fix things as best I can.
Isn't it funny because you're coming through very clearly for me? It was just specifically the camera.
Just the visuals
on the paper.
Okay.
Mm-hmm. But your
Okay.
voice was coming through fine.
Okay. Well,
at the minute, the service providers are rolling back internet speeds. That might be the issue on your end.
yeah.
Could be a case of they've rolled back the internet speed because obviously so many people are using it at the minute.
Yeah, I'm afraid I think that's almost certainly what it is. Thanks, Scott. And, you know, I guess maybe the solution in the long term will have to be that I go into work on a Tuesday because there they've got faster internet speeds. But particularly during lockdown, I'm trying to avoid too much traveling around London. So it's just getting the right balance. But I mean, that was useful. If people can just make sure they tell me and put it in the chat when things aren't working right, then we can try and fix those. The main thing to take away here is we drew out the joint at F. So I've written this to kind of remind myself I'm working on F. Then we drew the free body diagram of it, which involved tension in each of the, what I've done is to mark tension in each of the members that connect up. And then the final step is to use the free body diagram and the principles of equilibrium to write down some equations about what those member tensions must be. And in this case, because there's nothing pointing to the left, the force acting to the right has to be 0. And because there's nothing pointing upwards, the force acting to the right, acting downwards has to be 0. So we've got 2 bits of our answer already. And in fact, I can mark those on the diagram. That's 0 and 0 newtons tension, which also means 0 newtons compression in those 2 members. That's how we're going to work all the way through this. So let's go straight on and do the same thing for another joint. One of the things that you'll start to see is that this becomes slightly repetitive. And that is something that I really want to encourage you to embrace. As soon as you can turn things into a process in engineering, something where you just do the same thing over and over again, you've solved it. And then doing the process is just practicing. It's just, you know, getting on with the details of how to do engineering. But we've taken something that we didn't really understand and turned it into a set of steps that we can kind of turn a handle on and just keep repeating. So pick another joint. I've gone to A because I've already solved one bit of the puzzle at A. I know the force in this member is 0, and I guess it's reasonably simple otherwise. It's got 2 members connected to it, so it's easier than either E or B, and then I can kind of also be working from left to right. That's my thinking in picking A next, but I certainly could jump to C as another way of doing things if I wanted to. So no one right answer, I guess, is the key there. Okay, let's mark on A. There is the joint or the pin, and there are 3 members, which I'll immediately mark on as being in tension and therefore acting as a pulling force away from the pin. And for each of them, I'm going to label them as T for tension, followed by a subscript for whichever member I'm looking at. Everyone in this class is welcome to use their own notations and their own styles of answering things. I guess these ones have always worked for me, and it helps me if I know I'm using the familiar notation. I know that I'm working in my usual series of steps, and so I find that helpful. But you know, like I say, everyone should use what works for them, and this is only my recommendation. And we've got one more thing to mark on this free body diagram, which is this external force of 30 kilonewtons. Like that. And those are all the forces that act at A. There's one thing here that's just slightly trickier than the analysis we were doing at F. And that thing that's slightly trickier is that we've got one force at an angle. And I hope you all remember from earlier classes that when we've got a force at an angle, the easiest thing to do is to break it down into horizontal and vertical components. So that's what I'm going to do very quickly, is just to look at TAE on its own and break it down into horizontal and vertical components. Just looking at the directions on here, you can, the direction of TAE is the same, I guess, or the angles involved are the same as this angle here on my diagram. And this length and this length are the same length. So this angle is 45 degrees. And that's one of those ones you could use trigonometry on this triangle if you wanted to, and say the tan of this angle must be 1/1, so the tan of this angle is 1. But I would just remember that in these kinds of trusses, where you've got lots of bars the same length, horizontal and vertical, the diagonals will always be at 45 degrees. So yeah, two ways to do that, either by remembering or by trigonometry. Anyway, the important thing now that I've drawn out this diagram is that I can calculate V and H. I guess I can say sine 45 is opposite over hypotenuse, which is V over TAE. So therefore V equals TAE times sine 45. Similarly, cos 45 equals H over TAE. Cos is adjacent over hypotenuse. So therefore H equals TAE cos 45. You can put sine 45 and cos 45 into a calculator and they'll come out as 0.707. I'll just show you. Sine 45 is 0.707. There you go. It's also precisely 1 divided by the square root of 2 is sine 45 and cos 45. Some people remember that, some people don't, and I don't really mind either way. But I'm just going to say V equals 0.707 TAE and H equals 0.707 TAE as well. Elsewhere, I think in some of the worked solutions, I do use 1 over root 2 instead of 0.707. So that's where that number is coming from. Okay, let's go back and draw the diagram as well. Sorry, draw the diagram again, because what I'm going to do now is take out that force at an angle. I'll put in all the ones that are either horizontal or vertical, just like before. And now we can put in the two forces we just calculated, V and H. Sorry, it's just gone off the bottom of the screen. So this is now the diagram I'm working from. Now we can do the same thing that we did here and look at horizontal equilibrium and vertical equilibrium. I guess actually there's one more thing I can do, which is to remember we've already calculated TAF here and it equals 0. That's a calculation we did up here. So everything that we've used previously will keep coming around and using. And just for some clarity, I'm going to box all of this off like that to say that's a kind of side calculation that we've done now. Vertical equilibrium, I'll start with. You can do either order. Vertical equilibrium tells me that forces acting upwards, TAF plus V plus 30 kilonewtons equals forces acting downwards. There's none of those, so that's going to be 0. TAF we know is 0, plus V we know here is 0.707 TAE plus 30 equals 0. I'm going to move to a new sheet rather than try and squeeze this all in right at the bottom of a sheet. I've just written down 0 plus 0.707 TAE plus 30 equals 0. Rearranging all of that, I'll get 0.707 times TAE equals minus 30. TAE equals minus 30 divided by 0.707. And that's something I can now put into a calculator. And that comes out as minus 42.4 kilonewtons. I know it's in kilonewtons because this 30 here was also in kilonewtons. Good, so now I've got something else I can mark onto my diagram. This number here is minus 42.4. And at the start of the analysis, I said I'm going to assume everything's in tension, and if I get a negative number, that means it's actually a compression. So what we've learned is that this member here, member AE, is being compressed, and the magnitude of that compression is 42.4 kilonewtons. I'm going to keep on going, and then at the end we'll come back and look at what some of all this means. But on this joint at A, we've done vertical equilibrium. So the next thing we're going to do is to do horizontal equilibrium. And for that, we say forces acting to the left, well, there's none of those, equals forces acting to the right. And that's H and TAB. TAB plus H equals 0. Forces acting to the left, which is 0, equals forces acting to the right. And I've just flipped it round, well, because it makes more sense to me as an equation to say something equals 0 than to say 0 equals something. But we'd get the right answer either way. We also have an expression for H. That's in this calculation that we did here about the triangle at 45 degrees. And so we can say, okay, TAB plus 0.707 TAE equals 0, substituting in for H. And then we also know what TAE is, because we just calculated it in the last bit of the question, and it's this number I wrote on the diagram here. So TAB plus 0.707 multiplied by minus 42.4 equals 0. That gives me TAB minus 30 equals 0 when I put it into a calculator, and TAB equals 30 kilonewtons. So what we're trying to do always is to keep moving around the structure, calculating these unknowns. And we've got another one now that this force here in AB must be 30 kilonewtons. I go back and I mark it on my diagram there. This is good. We're making progress, and I appreciate that, you know, we're taking some time here. We've been going for over 20 minutes and we're just under halfway through the problem. So, you know, I know these are slow problems that take a long time, and that's fine. If you get them in an exam, you'll be given time to complete them. But it's a case of going through the steps over and over again, doing the same kinds of things. So now we're going to pick another joint to work on. We've analysed what's happening at F and we've analysed what's happening at A. If we look at B, it's still not that great because we've got one known force here, and in fact we've got another known force here, but we've got three unknowns, this one, and this one. If we look at E, it's a bit better. We've only got two unknowns, this one and this one. And in fact, that is good. Horizontal equilibrium and vertical equilibrium mean we'll have two equations, and you can calculate as many unknowns as there are equations. So two equations will get us two unknowns, and we'll be able to work out everything that's happening at E. So I'm going to move there next and do the analysis on that joint. Let's draw it all as we have it. This is TEF. This is TAE. This is TBE. And this is TDE. Those are all the members that connect into E, and so those are all the forces we're going to have to account for. And we know some of these things. We know this equals 0, and we know that this equals minus 42.4. That's what we just calculated. But we also know, kind of usefully, that if this is minus 42.4, this is minus 30, and this is minus 30. I'm just sort of undoing the work we did around this triangle here. I guess I'm going to leave that as an exercise for you to convince yourself of, if you want to, that if you analyze what's going on in that triangle, and the hypotenuse is minus 42.4, and this angle is 45 degrees, you'll get to minus 30 as the horizontal and vertical forces. The important thing, though, is that I can now swap TAE, which is at an angle, for a horizontal and a vertical force, and that makes everything much easier in the analysis. So let me just redraw my diagram with some numbers. This is just worth a slight pause here as well. One of the things that was in the very first lecture that we went through was the idea that in engineering, you're always going to be jumping between physics and maths, between a kind of understanding of what's really happening here and an understanding of the kinds of equations and numbers we can write down about it. And it's worth remembering that we said this 42.4, the minus sign just means it's a compression. So whereas I marked on this diagram that TAE was pulling away because it was a tension, it's actually going to be pushing up and to the right because it's a compression. And that means where I've marked these -30s, what I really mean is the force isn't to the left at all, it's +30 to the right. And again, that kind of translation, that a negative force in one direction is the same as being a positive force in the other direction, is the kind of thing that comes with practice. In any case, as long as I write things consistently, I can have a negative force to the left and just fit that straight into my equations. So that's what I'm going to do here. Horizontal equilibrium. And again, I'm using this same sign always to indicate that I'm doing horizontal equilibrium. Forces to the left, that's -30, equal forces to the right, that's TDE. And now I guess you can see that's great. If I just rewrite that the other way around, TDE equals -30. We had almost no work to do and we've calculated another part of our answer. And I can mark that on my diagram. This force here is -30. If I do vertical equilibrium, I get forces acting upwards must equal forces acting downwards. I'm actually going to do it the other way around and say forces acting downwards, that's TBE plus -30, equal forces acting upwards, that's 0. And when I rearrange that, I'll get TBE equals 30. These are all in kilonewtons again. Every number I write is going to be in kilonewtons. So that's another answer, another unknown force that we can mark on our diagram. And things are starting to get quite well annotated now. We've worked out what many of the member forces are here. That's all the analysis I can do at E. I know all the forces in all the members connected to E. So now I can choose another joint to work on. We're pretty close to the end of this problem. And I can choose to work on either B, D, or C. There are at this point advantages to all of them, and you could choose whatever you want. It doesn't really matter. I'm going to go with D. Just it looks a little bit simpler than the other ones to analyze. So I hope at least you all now can predict the process that I'm about to go through. I'm going to mark that I'm looking at the joint at D, and then I'm going to draw a picture of the pin at D on its own with some forces marked on. And those are all the members acting, all the members connected to D, and so those are all the forces that can be acting at D. Usual thing then, I'm going to just take this force that's acting at an angle. Again, it's at 45 degrees, and mark it onto a diagram where I can split it up into horizontal and vertical components. And it's exactly the same triangle as before. And in fact, we'll see this triangle a whole lot. Sorry, that says 45 degrees. I know it's kind of come out small. But the important thing is we can use the same outcomes as we had on this previous triangle here. H is going to be 0.707 times TBD, and V is going to be 0.707 times TBD as well. And now I can redraw my diagram using only horizontal and vertical forces. That always helps. And also I know TDE, that's marked on my diagram, and that's -30. So that's my new diagram. All of these forces have drawn them in a slightly offset way, but they're all acting on the pin. It's just I've now, because I've substituted this force for a horizontal force and a vertical force, I've got 2 horizontal forces now and 2 vertical forces acting on that pin. And then again, the usual format of answer. If we look at horizontal equilibrium, forces acting to the left, that's H plus minus 30 equals forces acting to the right. I haven't marked any forces to the right. H, I know I can substitute, that's 0.707 TBD minus 30 equals 0. 0.707 TBD equals 30, and therefore TBD equals 42.4. I'll do that in all its steps. Divide both sides by 0.707. TBD is 30 divided by 0.707, and that, when you put it into a calculator, is 42.4 kilonewtons. And that is positive, which means it's a tension. I can mark that onto my diagram as well here. We're nearly done now. I can do vertical equilibrium here, which tells me that forces acting downwards, that's V plus TCD, equal forces acting upwards. There are none of those on my diagram, so that's 0. I've got an expression for V. It's 0.707 times TBD. And I know what TBD is. It's 42.4 kilonewtons. So 0.707 times 42.4 plus TCD equals 0. This comes to 30 when you put it into your calculator. So you'll get TCD equals minus 30 kilonewtons. And I can mark that on my diagram. And now there's only one thing that we don't know. It's this member here and what the force is in that. So let's do a final bit of analysis at C and see how we get on. And then we'll come back. The plan now is this question will be done in about 3 or 4 minutes. Then I want to spend about 5 minutes just thinking about what we've done and kind of going back to the big picture, because while you're working through a question, you end up sort of lost in the detail, and it's useful to go back and look at what we've learned. So that's about 10 minutes more, and then once we've done that, we'll take a break. Okay, so I said I would look at C, and same steps as always. Draw the diagram with outward arrows for each member. And remember here that there's also the external force that we calculated at the start to be 30 kilonewtons. So that's what's happening at joint C. This is nice and easy to analyze because there are no forces at an angle. Everything's horizontal or vertical already, so we don't need to do any trigonometry to start with. We can just say vertical equilibrium tells us that TCD plus 30 must equal 0. Forces acting upwards must equal forces acting downwards. So TCD is going to be minus 30 kilonewtons. That's good, because that's also the same answer that we got when we analysed what was going on at D. And you should always, no matter what joint you pick, you should be finding the same stressors within each member. And horizontal analysis says that forces acting to the left must equal forces acting to the right. And so TBC equals 0. And that was the last unknown on my diagram, and I can mark on that force. So let's just pause there and look at this diagram. I'll move all the other stuff out of the way so it's not in danger of confusing anything. What we've really done is to calculate 9 different things here. That's why it took a long time, because we weren't just working out one answer, we were working out 1, 2, 3, 4, 5, 6, 7, 8, 9 answers. And you know, sometimes that's just what we have to do in engineering. We have to do quite a few calculations rather than immediately being able to jump to the answer. But what we've got now that we've done all of that is something really very useful. We know the force in each different member of this truss, and if they were all made out of the same material and all had the same cross section, so if they're kind of all the same steel bar that's being used, then we can see very quickly the ones that are likely to break are the ones with the highest forces, and that's these 2 diagonal members. And in fact, this one here is in compression and this one here is in tension. So we could even look and see, is this more likely to collapse in tension or in compression? And we could start doing analysis to see when this truss breaks, where is it likely to actually break, and then maybe reinforce that that bit of the truss. And then that takes us back in an interesting way to the photo we looked at 2 lectures ago when we were doing stress and strain of the crack in the Forth Road Bridge and the solution to that crack that we talked about at the time, but that doing this kind of truss analysis would have told us perhaps that that is the bit of the truss that's supporting the highest load, and therefore we might have known in advance if we're going to reinforce that bridge, we want to reinforce it there. So we could have done much more to predict what went wrong when that crack appeared in the Forth Road Bridge. Okay, that is a kind of big picture look at what we've learned. We've learned that some of the members have 0 force in them, some are in compression and some are in tension, and we can calculate all of those things, and we can calculate the magnitude of the forces. And the way that we did that was by taking each joint in turn, picking an order slightly based on experience and slightly based on guesswork. But for each joint, we were able to draw a free body diagram and then use horizontal and vertical equilibrium to write down some equations. And each one of those new equations we can write down helps us find one new unknown. And so we work our way through the problem. We had 9 unknowns, so in the end we needed 9 equations. You'll see we've actually come up with 10 equations, 2 for joint F, 2 for joint A. Try and pick up my paper without knocking my camera over. 2 for joint D, 2 for joint E, and 2 for joint C. The reason we needed 9, we've got 10, and that's why we ended up duplicating one answer. We found TCD once here and once there. So everything in the end makes a kind of systematic sense. That's quite a long bit of analysis, and you know, if you're thinking, hang on a minute, what was going on there, I'm sympathetic to that, and the key thing is to make sure that you're practicing this, and also just maybe to make sure that you agree that I was always following the same set of steps for each joint, and then once you're happy that you have to write down that set of steps, it becomes a matter of practice to get used to actually just doing those steps. I'm just going to throw it open for questions, discussion, or feedback before we take a break. Okay, that seems pretty quiet. Can everyone just put their hand up so I can check that I do at least have a video connection still? Fantastic. That's good enough, and that was a majority of the class able to do that. So that's great. Okay, in that case, what I'm going to recommend is we take 5 minutes. If you want to put any questions in the chat or any discussion in the chat, that's great, and we can come to that once we've had a break. But let's take that break now. Okay, that's been 5 minutes. I've put in the chat just kind of the 7 steps that we followed there. And it's one of these processes that has a loop within it. So at step 7, you go back to step 2 and then do the whole thing again. And that's about each time going back and picking a new joint and solving, writing down the equations for that joint, solving the equations for that joint, learning something new about the structure, and then going back around again to the next joint, and so on. Okay, that is the method of joints. The good news is once you understand what we did in the first hour there, you've really got that nailed, and it doesn't get more complicated than what we've just done. It's always the same process. And now I want to talk about something that's similar but kind of even broader, and I think it's an easier technique to understand and to learn and to use, but I think it's worth starting with the method of joints because the method of joints has a more systematic way of working with it. So I'll stop talking and I'll start showing the slides. They are here. And I think I should be able to full screen for a bit as well. So we did the method of joints, and now we're going to look at what's called the method of sections. With the method of joints, we looked at individual joints, and I said, for example, this pin at A, the circle here, must be in equilibrium because it's not moving. So it must be on its own in equilibrium, and therefore we could draw out a free body diagram for the pin at A. But that's true no matter where we choose to kind of draw the boundary of our free body diagram. We can imagine that we've isolated any part of this truss, not just the circular joints, but any bit we choose, and that whole bit must be in equilibrium. It must be not moving. And that's the method of sections. And you can kind of think of a section as being an imagined cut. So what we're going to keep on saying is we can imagine that we make a cut in the structure at a certain point or through a certain bit of the structure, and then we can mark on all the forces that might apply at that cut. And those are our unknowns, and then we've got something that's in equilibrium that we can solve for. So just to go back quickly here, the method of joints, we took this joint at C and we drew a free body diagram for it. You could sort of say what we've done is to make an imaginary cut right around C and then to mark on all the forces that could be acting. And let's say here we wanted to know about the forces that act in AB or BE or EF. We can make our imaginary cut go through all of those and then mark on the forces that would be acting at that cut. So wherever you slice through something, that member can have a tension inside it, and so you have to mark that tension on your diagram. So I've marked 3 forces here, all pointing away from the cut. So they're all in tension, and we'll do exactly the same things that we've always done before, but now we're looking at the equilibrium of this whole thing here. So we've got a force acting downwards, 2 forces acting to the right, and 1 force which acts upwards and to the right, and we'll be able to use equilibrium to try and find those things. This time we're going to use 3 types of equilibrium. So that's where this is slightly more complicated. In general, I think this is an easier technique, but now we need to think not just about horizontal and vertical equilibrium, but also about moment equilibrium. And that means that we'll be able to solve for 3 unknowns because we'll have 3 equations. And so it's good, if you can, to try and slice through 3 members, because 3 unknowns will get us 3 member forces. And then this is what I've already said about the method of joints. The easiest thing to do is to always assume things are in tension. And if you get a negative value, that means it was compression. So what does that look like in practice? Well, we'll do this example. The good news is this example isn't going to take us 45 minutes. In fact, we can get through it pretty quickly, but we'll start by doing the same thing as before. So I'll get everyone to take 3 minutes now, please, just to draw out this diagram, mark on anything that you can see or calculate immediately, and then we'll look at the method of sections in about 3 minutes time. And I'll draw out my diagram too. Okay, that's about 3 minutes. What were people able to mark on their diagrams?
The upward forces are made for 1,000 million.
Yeah, exactly right. Good. So there has to be equilibrium on the overall structure. We know that there's a downwards force which adds up to 1,000 newtons. So we know, therefore, there must be an upwards force that adds up to 1,000 newtons. And we can draw a line straight down the middle that's a line of symmetry. And the forces, the two 500s are symmetric about that line. So I'm going to say that these two upwards forces must also be symmetric and I'm going to say they're both 500 pointing upwards. Again, just if you wanted to, you could do an analysis where you maybe take moments about D and mark this as an unknown force and then calculate things that way. So you could get to this answer by calculation rather than by visualization. But I think one of the greatest tools in an engineering toolbox is understanding symmetry. And so anytime we can, we'll try and take advantage of when things are symmetric. Okay, now the question actually says find the forces in AB, that's here, and in AE, that's here. So I'm going to make my cut go through those two, and then I guess I'll go through here as well, and see how I get on with that. That's how the method of sections works. You find the bits you want to target, or you want to know about what's happening inside something. So we want to know what's happening in AB and in AE. And then you kind of make your imaginary cut go through those bits you want to know about. And then you draw out the structure as cut through. So in this case, that looks like this. That's about how I've cut it up, I think. And we don't know what's happening in each of the bits at the cut. So they can be represented by forces. This is TAB. This is TAE. And this is TDE. And those are my unknowns. So three unknown forces, which I've marked on my diagram. And now what I can do is to start doing the same thing that we're doing a lot of at the moment, which is looking at horizontal and vertical equilibrium. Starting with vertical equilibrium, just because I can see I'm going to get a really nice equation out here. Forces acting downwards, well, I've only got one of those, equals forces acting upwards, and I've got one of those. So already I've got to one of my answers. The force in AE is 500 newtons and it's in tension. If I now do horizontal equilibrium, I'll get that forces acting to the left, well, I've got none of those. I've marked on 4 forces on my diagram. 2 of them are to the right, one is up and one is down. There's nothing acting to the left. So 0 equals forces acting to the right. That's TAB plus TDE, like so. So what we said is we'll actually, in the method of sections, be able to use a third tool, which is to look at moments. And if you remember, with moments, we have to choose something to take moments about. And I'm going to choose this point here, which is D. It's that same D from there. So taking moments about D, we've got 4 forces that we might have to think about. Each of those could contribute to the moment. Remember that we said forces that go through the pivot, so through D, don't add anything to the moment, because a moment is a force times a distance, and the distance involved here is 0. So this force adds nothing, and this force adds nothing, because the line of both of them goes through D. So we're interested in the effects of these 2 forces here and how they contribute to the moment. And for each of them, we need to think about the distance back to the pivot. If I just draw out a quick diagram just isolating those two things. Then that's involved for TAB is this length here. It's the perpendicular distance back to the pivot. And the distance that's involved for TAE is this length here. Also, the perpendicular distance back to the pivot. I'll call those L1 and L2. That's where it's worth just going back to the lecture on moments on its own and making sure you're really happy with that, because now we're involving it in a larger analysis. It's going to be tricky if you're struggling to think about the moments calculation in the middle of a bigger analysis. It'll make the bigger analysis much harder. So it's worth just being completely happy with the moment calculation. From the diagram that's on the left-hand side of the screen at the moment, L1 equals L2 equals 5 meters. In both cases, the moment arm is 5 meters. The distance involved in the moment calculation is 5 meters. And they're both going to act clockwise. Both of those forces will tend to pull my pen in this direction. And that's clockwise. So TAE times 5 plus TAB times 5 equals 0. The two clockwise moments are the only things that contribute to a moment, and they must add up to 0. We know TAE, it's 500 newtons, so we get 500 times 5 plus TAB times 5 equals 0. So times TAB equals negative 2,500. So therefore, TAB equals negative 500 newtons when you run through that calculation. And again, that's an answer. We weren't asked for TDE in the question, but we pretty much calculated it anyway. So we can just, as an aside, make a note, 0 equals TAB plus TDE. That's what we wrote down for horizontal equilibrium up here. And we now know TAB is minus 500. And that means TDE must be 500 newtons. So we've got 5 numbers we can write down on our diagram up here. This TAB is minus 500. That is, it's 500 newtons in compression. This TAE is positive 500 newtons in tension. And this TDE is also positive 500, so 500 newtons in tension. And we've calculated everything that we were asked in part A of the question. So I hope you can see that was a quicker analysis than what we did in the last method of joints analysis. And that's usually an advantage of the method of sections. You can target the results you want to get to. There's one thing that we've done a lot of today that's just worth flagging or mentioning just now, that we keep going back and using answers from earlier in the question. So here we had an equation that we'd written down correctly, which had 2 unknowns in it, TAE and TAB, but we'd already used vertical equilibrium to calculate one of those things. So we knew TAE. So sometimes if you can't see how to move a question on, it's worth just going back and seeing if some of the unknowns in your in your calculation are things you've already calculated somewhere further up the page. The part B in the question says, what other forces can you now state? Does anyone have any suggestions there? I guess the thing to go back and remember is that we've mentioned that this whole system is symmetric. It's got a line of symmetry down the middle. Both of these supports can only provide upwards forces in this case, because there are no horizontal forces acting on the whole structure. That's a kind of slightly complicated detail, but the important thing is that everything is symmetric about a vertical line through B. So if I know AB, AE, and DE, I also know BC, CF, and FG. And by doing this analysis, we've worked out most of what's going on in the structure. So the method of sections can be very powerful, and the use of symmetry can also be very powerful. Okay, that's that question complete. I'm just going to go back to full screen and summarize that. We used two different methods today. The first was the method of joints, and the second was the method of sections. Both of them rely on assuming that we're looking at a truss, and that the truss is made up of members. And by members, I mean kind of long, thin bars that can only be in tension, I should say, or compression. Sorry, I've just spotted that typo. So only in tension or compression. And this slide gives a quick summary of what we did in the method of joints and what we did in the method of sections. Okay, so those are the two techniques that we wanted to learn today. And now it's a case of sort of going away and practicing them. I think they turn out to be very useful. But one thing that I just wanted to discuss before we leave that side of the class for now, if you remember when we started looking at stress and strain, the first bit of the lecture was about springs, and then from springs we were able to go to a much more general set of tools about stress and strain, starting from understanding Hooke's law and how springs work. Lecture is a bit like that. If you're tempted to think there aren't that many trusses in real life, most things aren't a truss, just trust me a bit that everything is a truss if you look at it in the right way. And that this kind of analysis, if you really understand particularly the method of sections, you can understand the internal forces in almost anything. And in turn, that means you can work out when almost anything is going to break. You can see then that it's going to be something really engineering, because what they're doing is building up the set of analysis tools that overall will tell us, is this thing strong enough, or do we need to make it stronger? And that's one of the big things that engineering designers can do. So that's kind of why we're here today, and why we've done that analysis. Don't just think it applies to quite simple pictures like the trusses we've been looking at today. In a different sense, it applies to everything we might want to analyze. Any questions or thoughts or feedback at this stage on anything we've done today? Okay, good. Well, as always, feel free to put things in the chat and to talk about things that way, if it's helpful. That is the lecture content for today done. And I do kind of want to stop there. I know that it's quite an intense lecture, and it feels like you're doing quite a lot of maths working along with me. So I just want everyone to now have some time for that to sink in, and then maybe to go away and look at tutorial sheet 4, where there are some examples that are very similar to these ones that you can go through and try out. But the other thing that I just want to do for today, moving to something completely different, is today's quiz, which is at the bottom of the Moodle site for the lecture we've just been through. So these are the slides. If you click on truss analysis, you'll see the slides we've just been through. If you click on the worked solutions, you'll see my previous worked solutions to all of this. And I may do something slightly differently, so do go and have a look at those and see what they say. They might be helpful. There's some recommended reading, which is specifically where in the Bird and Ross textbook that we've talked about this comes up. And then there's this week's quiz, which is week 5. I managed to set it up now so that everyone gets 7 minutes. So start anytime now, and I'll come back in 7 minutes and we can have a look at it. If there's anyone who's got any VLE problems, let me know that as well, and we can keep on trying to fix those. Okay, that's mine timed out. So I'm going to assume everyone's had a chance to have a go at that. And let's just, I'll share my screen and we'll go through it. Feel free to jump in if you've got questions or things that you weren't sure about or want to clarify. So I hope everyone can see the quiz. My feeling is a lot of people remember this one, that with a magnet, magnets have two poles, north and south, and opposites attract in magnets. So north attracts south in both of these cases in A, but similar repels. So north repels north, south repels south in B. And I guess it's interesting that magnets are in this quiz, or it's interesting to me. We used to have a colleague called James Barnum, who was a designer, a real engineering designer who actually made very practical things that people wanted to use. He went on Dragon's Den with a system to stop people's baths from flooding, for example. And he was very good about realizing the power of magnets for design, because in a way, when you use static magnets or fixed magnets rather than electromagnets or anything, when you use the kinds of magnets that people think of when you say magnets, there's almost no force when they're a long way apart, and then when they get very close, you get this quite large force between them. And that can help you to do all kinds of things. I mean, obviously, we see magnets used for door catchers in kitchen cupboards and things like that, for example. But if you always just have in the back of your mind, can I design this better if I include magnets? It'll just add another string to your kind of engineering design skills, I think. So that's that one. Question 2 about flagpoles. This is an interesting one to come up now. Next week, we'll just be looking at some questions that are really quite closely related to this. The important thing is that the biggest stressors in the flagpoles, the place where it's most likely to break, is right at the ground or very close to the ground. And most people, again, have an intuitive sense of that. If you imagine these breaking, you would picture them breaking somewhere towards the bottom of the pole rather than right up at the top. In fact, you can see it would be quite hard to cause this flagpole to break near the top. And so the kind of secondary bit of intuition there is the ones that are thickest at the bottom will tend to be the strongest. And in this case, that's A. You can see in some of the diagrams how we could do computational analysis to try and get to those answers. But as I say, we'll also look at doing some kind of first principles analysis that helps us to understand that. So these kinds of questions, you may have an intuitive sense already, and then throughout your degree, we'll look at kind of putting the modeling and the structure behind that. Question 3 I like a lot because I'm quite proud of my fusion work here to produce a reasonably clear diagram of it. What's going to happen, the important thing to understand in this system is this little hinged flap here. And I admit it takes a while just kind of looking at the picture to work out what every different part is doing. But this flap that can go up and down means that whenever you push down on the plunger, if the pressure increases down here, the flap will just open and that will release the pressure. But when you pull up on the plunger, this flap will be closed and it can't be pulled further in that direction. So it'll stay closed. So when you push down, all the air will vent out through this little hole in the system here. But when you pull up, there'll be nowhere for the air to go, and so you'll get suction when you pull up, and that means that eventually the water will all be sucked out of this cup here. So that's what this system is doing. If it wasn't obvious to you, it probably means that my fusion drawing isn't quite as good as I thought it was. So don't kind of, don't worry if this system wasn't clear to you. But do now, just once you've seen the answer, go back and have a think about what it's doing and how it all fits together and how it works. Because these kinds of things are useful to understand. This is the kind of question that turns up a few times in these questions. Just you have to be able to visualize pulleys and belts. The crossed belt here will mean that if this one turns clockwise, if the green one turns clockwise, this pulley here will turn anti-clockwise. And this is not a cross belt, so that one will turn in the same direction. So that will turn clockwise. Sorry, let's start again so I can be clear. The green one turns anti-clockwise, that's in the question. The crossed belt means this one here turns clockwise. This one turns in the same direction as that one. A straight belt means two pulleys will turn in the same direction. And you can experiment with all these things at home. Get some string and some cut some discs out of cardboard, or use tape or all kinds of things just to test out pulley systems and see how they work. That's a great bit of physical experimentation. Anyway, these two both turn clockwise. If the green one turns anti-clockwise, then this one here turns anti-clockwise, which means this belt is going up on the left-hand side, which means all three of those small ones turn clockwise. I think easier than me describing it is to watch the animation and see if you can, if that matches your understanding, then that can be useful. And the last one, I did have it pointed out to me that it should really say which weight will pull the other one up or which weight will move, but the answer is neither. So the answer is C. And one of the ways that you can work that out is to use the method of sections. So if you imagine taking your section through the rope here, then the force that must act on the left-hand side of the rope must be equal to W in order that this side stays in equilibrium. And the force that must act on the right-hand side of your cut must also be equal to W so that this side stays in equilibrium. So everything all the way along the system is, all of the tensions in the rope, the tension at any point in the rope is equal to W, and that means the whole thing stays in equilibrium. So that was this week's quiz, and I hope people found that made some kind of sense when we talked about it, and I'm happy to go through any of it that people would like to. Otherwise, that is everything we wanted to cover today. So I guess just to close out by saying, does anyone have any questions or anything that they want to flag up about anything to do with this module, or in fact the course or your university experience? Okay, good. I know it's all quite involved, so one of the things that I'll do is to make sure that the video is available, as always, on Moodle. All of the videos so far are linked from the Moodle site. Every lecture is there in a section called lecture videos. So, if you do want to go back and look again at moments, for example, that's in there, and you can go and find that. And there are still tutorials available to do on the Moodle site. Those aren't assessed but they are just useful practice and a useful way to check that you're on the right track. And later in the module, we can find some time to work through those tutorials. Okay, I'm going to stop the recording now. I'll stick around, and if people have questions to put in the chat, then I'm happy to answer anything that comes up in the chat, or happy to talk as people are leaving the class. But otherwise, good to see you all this week, and I'll see you again next week. And have a great week.
Thanks. See you later.